Superman isn't the only one with X-ray vision. Plenty of exploding stars are also adept at blasting outbursts of this high-energy light. Now, thanks to a chance discovery, scientists are aware of an entirely new explosive stellar source of X-ray radiation. These outbursts' light output didn't resemble any previous cosmic explosion. Meet the Millinovas, a term that will now undoubtedly make its way into the lexicon of space enthusiasts. In a new study, astronomers discovered 28 of Millinovas in the Large Magellanic Cloud and the Small Magellanic Cloud, two satellite galaxies of the Milky Way. They then discovered that the first of these explosions may have been spotted 8 years ago, but wasn't identified. Though the scientists don't quite know how these events generate X-rays, they believe millinovas are caused when dead remnant stars called white dwarfs feed off a swelled-up companion star. We came across a group of outbursting variable stars exhibiting very characteristic triangle-shaped symmetrical outbursts that did not resemble any previously known variable stars, team member and University of Warsaw scientist Przemek Mraz told Space.com. We found this new group of stars by chance. The team was searching 20 years worth of data from the optical gravitational lensing experiment for long-duration, light-curving, gravitational microlensing events that could indicate the presence of black holes left over from after the Big Bang, so-called primordial black holes, in the halo of dark matter that surrounds the Milky Way. Over the past months, I have been working on a project aiming to search for signatures of massive primordial black holes in the Milky Way dark matter halo, Mraz said. We did not find any, which demonstrated that such massive black holes might make up less than a few % of dark matter. Ordinarily, this may have disappointed the team. But the result led to the discovery of these strange stellar X-ray sources, now known as millinovas, or more correctly, millinovae. The OGLE data revealed several objects in the LMC and SMC that brightened by between 10 and 20 times over the course of a few months. Some even showed repeated explosive outbursts as frequently as once every few years, while others only exploded once during the observation period. One in particular, designated OGLE M-Nova 11, which erupted at the end of last year, allowed the team to perform a detailed study of these objects. In November 2023, one of the objects entered an outburst state, so we decided to carry out some additional follow-up observations to study it in more detail, Mraz said. We obtained a set of optical spectra with the Southern African Large Telescope, SALT, telescope. We found emission lines from helium, carbon, and nitrogen ionized atoms, indicating extremely high temperatures. Mraz added that the researchers also observed this object with NASA's Neil Gehrels Swift Observatory, which detected soft X-rays coming from the source. The team theorized that these X-rays were produced by a gas heated to the temperature of over 1 million degrees Fahrenheit, or 600,000 degrees Celsius. That is about 3 times hotter than the hottest known star in the universe, WR102, and 100 times hotter than the surface temperature of the Sun. If OGLE M-Nova 1 had occurred in our solar system, it would have been 100 times brighter than the Sun from our perspective. What these 28 events resembled was a strange and, until now, seemingly unique cosmic explosion called Assassin 16-0, which was detected in 2016 by the All-Sky Automated Survey for Supernovae, and which the team now thinks was a millinova. We believe OGLE M-Nova 11, Assassin 16-0, and the other 27 objects form a new class of transient X-ray sources, Mraz said. We have named them millinovae, as their peak brightness is roughly 1,000 times lower than that of classical novae. So, what exactly are millinovas, how are they created, and what sets them apart? Despite the lack of similarity between classical novas and dwarf novas, white dwarfs do seem to be behind the millinova mystery. These stellar remnants are created when stars with masses similar to that of the Sun exhaust their fuel for nuclear fusion, the process that converts hydrogen to helium in their cores. As nuclear fusion proceeds in the star's outer layers, it swells up as a so-called subgiant or red giant star. Unlike more massive stars, whose immense gravity results in the creation of neutron stars or black holes after death. Stars like the Sun end their lives as smoldering white dwarfs, superdense objects to be sure, but not on the same level. While this is a peaceful death for solo stars like the Sun, many stars have binary partners that can grant them at least a temporary resurrection. That's because some binaries are close enough for the white dwarf to begin pulling material from their companions, causing them to spring back to life. In other instances, the star and the white dwarf aren't close enough to initiate this mass transfer until the companion star swells up as a red giant and fills its half of an imaginary figure 8 shape, or its Roche lobe. White dwarfs obtaining stellar material in this way are already known to be responsible for different nova events. The most famous of these are Type I supernovas, in which the white dwarf is obliterated in a runaway thermonuclear explosion after stolen stellar material piles up on its surface, though there are rare events called Type IAX supernovas, in which the white dwarf lives on as a wrecked zombie star. However, the team found that the optical light and X-ray properties of OGLE M nova 11 did not really match those of classical novas or Type I supernovas created by the thermonuclear explosion of a white dwarf when stellar material is dumped on its surface from a companion star. They also differed from the characteristics of dwarf novas, which occur in similar circumstances but are fainter and less destructive and can thus repeat. We think that Millinovae are binary star systems composed of a white dwarf and a subgiant star, a star that has exhausted the hydrogen in its core and expanded, Mraz said. The two stars orbit each other with a period of just a few days. Their proximity allows material to flow from the subgiant to the white dwarf. The University of Warsaw researcher added that, while it is currently unclear how the X-ray emissions of millinovas are generated, he and the team have 2 initial ideas to work with. According to one hypothesis, the X-rays might be produced in a belt around the white dwarf's equator, where the gas from the subgiant hits the white dwarf surface, Mraz explained. Alternatively, the X-rays may be coming from a weak thermonuclear runaway on the white dwarf surface that is triggered by the matter falling onto the white dwarf. The explosion is weak enough that little or no matter is ejected from the white dwarf. If that's the case, the white dwarf should be growing in mass, which could mean that it eventually erupts in a more powerful Type I supernova. Thus, millinovas could be Type I progenitors, an exciting development if true. Type I supernovas are incredibly useful to astronomers because their uniform light output allows them to be used as standard candles for determining cosmic distances. Getting a tip-off as to when and where a Type I supernova is about to blow via a millinova would help understand these events better. Mraz explained what's next for the investigation of millinovas. We will monitor the brightness of all 29 objects in real time and wait for the next outburst to start, he concluded. We also plan to carry out more follow-up observations better to understand the physical processes responsible for these outbursts.